Okay, so let's do 12.2. So definition, the derivative of a vector valued function is r prime equal to limit h goes to 0 of r of t plus h minus r of t over h whenever this limit exists. Okay, so this looks identical to the Math 150 or the single variable calculus definition, except we have an I, j, and a k component. Okay, so again, since it's a vector valued function, it means the r looks like f1i, f2j, f3k. So if we look at our definition here, then it's going to be r of t plus h. So I'm going to put t plus h in place of the f1, f2, f3 first here. Then subtract r of t. R of t is just the f1, f2, f3 divided by h. Then I can group the f1s together, and I can group the f2s together and the f3s together, and I'm going to distribute the limit also. So write it here. Okay, so I split it up into three separate limits. So the limit with the f1s, limit with the f2s, and limit with the f3s. And this is just definition of derivative of f1. This is definition of derivative of f2. This is definition of derivative of f3. So let me write that here. Okay, so we get derivative of f1, f2, and f3. So you can see then the derivative of our vector valued function is just a derivative of each of the component functions. So I have shown it here. Okay, so next thing. Okay, so the derivative of r, here's different ways you can denote it. You can denote it as d over dt, or r of t like this, or dr over dt, or capital D subscript t of r of t. They all denote the derivative. So your book may use these notations interchangeably. Okay, so now let's look at some properties of derivatives here. Okay, I'm going to erase this now. Okay, so here are some properties of derivatives. So let r of t and u of t be differentiable vector valued functions. Let w of t be a real value differentiable function, and c a scalar, so some real number. So the first property says if you take derivative of c times r of t, you can pop the c out in front, just like the single variable derivative from Math 150. Second one says the derivative distributes, so I guess the proper terminology would be it's linear. So you can kind of distribute the derivative to the first guy and then to the second one. And that's what this is saying over here. Oh, property 3 is, so w here is a real value function. So this is stating it's pretty much a product rule right here. So first function times derivative second plus derivative first times second. And then property 4, it's pretty much the same as property 3, except this time we have a dot product because both r and u are vector value functions up here. So when you dot them, the product rule would still hold here. It's basically saying. Then property 5, if we replace now the dot product with a cross product and take derivative in front, still this product rule still holds. So you'd have the first cross the derivative second plus the derivative first cross the second. Okay, property 6 down here. So property 6, so it's like a composition here. You're going R composed with W. So this is a chain rule right here. So we call the chain rule from Math 150 or single variable calculus. And property 7 says if RT dotted with itself is some constant, that means that R dotted with R prime has to be 0. Okay, I'm not going to prove all of these properties here. I'm going to prove property 4 and 7. So let's look at the proof of property 4. So I'm going to erase this now and write my property 4 up there and we'll prove it. Okay, so let's do that. Okay, so let's look at the proof of property 4, which is the product rule holds for a dot product. Okay, so our r is equal to f1i, f2j, f3k, u is equal to g1i, g2j, g3k. So we need to prove this result here. So let's first let's look at this side right here. So let's make an observation. Okay, so I went r dotted with u, so it'll be f1 times g1, f2 times g2, f3 times g3. And now the f's and the g's are real value functions, so they're like Math 150 functions. So we can apply the product rule to each of these. Okay, so let me do that. Okay, so again, I'm going to right here apply product rule from Math 150. So again, Math 150, if you haven't taken it at this school, it's a single variable calculus. So we're applying the single variable calculus product rule to this guy, this one, and this one. Let me write the result down here. So applying a product rule, we get this. I'm leaving off the t, like here at f1t, I'm just writing as f1 here, just for ease of notation. So the product rule on the first one, on the first product here, would be f1 times g1 prime plus f1 prime times g1. Then apply the product rule here and here. That's how I got these guys. Now I'm trying to prove this up here, so I have to make this guy look like this now. I'm going to rearrange some terms, so let me do that. Okay, so I've underlined these first three guys here. I want to put those beside each other, and the double underlined ones I want to put beside each other also. So let me write the result on here. So we get this then. So we have f1, f2, f3. That's going to be my r up here. Then I have g1 prime, g2 prime, g3 prime. That's going to be my u prime here. So let me write what this equals in here. So we get this, and that's what we're trying to show. Again, this one over here would be f1 prime, f2 prime, f3 prime. That's going to be r prime. And then you have your u, which is g1, g2, g3, and you're dotting them. So it'll be r prime dotted, this would be dot here, dotted with u. So we're done with the proof of this. Okay, now let's look at the proof of property 7. Okay, I'm going to erase this now. Okay, so the proof of property 7, so we're going to suppose that RT dotted with itself equals some constant. We need to show then that RT dotted with R prime of t is equal to 0. Okay, so let's first now take derivative with respect to t on both sides here of star. Let me write that. Okay, so taking derivative, we get this. And now the derivative of a constant 0, so this side is going to be 0. And we're going to apply property 4 to this with my u being r in this case. So let me do that. Okay, so again, derivative of constant of 0 will be 0 on this side. And applying theorem 4 to this, so it'll be r times derivative, dotted with derivative of u, but u here is r, plus r prime times second function, or dotted with second function. And properties of dot product, you can switch those around there so they're both the same. You can be two of those then. So right, next step. Okay, so I get 2 times r dotted with r prime, divide both sides by 2, and you'll get this then, which is what we're trying to prove. So we're done with property 7. So we're done with this. Now let's take a look at an example. Okay, so our example is from practice quiz 2 is actually question 1 continued. We already graphed this guy. So it says for the vector value function r of t equals sine ti, cosine t, j, t squared k, find r prime dotted with r double prime and r prime cross r double prime. So let's first find r prime and r double prime. Let's do r prime first. So it'll be derivative of sine, cosine, derivative cosine minus sine, derivative t squared 2t, so let me write that here. Okay, so here's our prime. So again, derivative of sine, cosine, derivative of cosine minus sine, derivative of t squared, 2t. Let's do now the second derivative. So it'll be derivative of this guy. So the derivative of cosine minus sine, derivative of minus sine, it'll be minus cosine, derivative of 2t would be 2. So I'm going to write that here. Okay, so I have it here, my r double prime. So again, derivative of cosine would be minus sine, derivative of sine would be cosine, there's a minus sign in front, derivative of 2t would be 2. Okay, now we have to dot these guys, so it'll be cosine times negative sine minus sine times minus cosine 2t times 2. Let me write that here. So dotting, again we go cosine times minus sine, which I have here, negative sine times negative cosine, two negatives will be positives will be sine cosine, 2t times 2 will be 4t. And notice these two will cross off here. So our answer then is just equal to 4t. Okay, so that's part A done. Now part B, you have to cross these guys, so let's write our definition of cross product right here. Okay, so here's my cross product definition. So I have my r prime on top, so it's going to be cosine negative sine 2t, and then my r double prime, which is minus sine minus cosine 2. Okay, let's do the I component first. So it'll be negative sine t times 2 minus 2t times minus cosine. Let me write that here. So I'll get this then. So again, a negative sine times 2 would be minus 2 sine, then minus minus. So this will become a plus here. Let's do the j component next. So I'm going to cover this. And this time we'll have a minus sign. It's going to be cosine times 2 minus 2t times minus sine t. Let me write that here. So we get this then. Okay, so lastly, let's do our k component. So it'll be cosine times minus cosine, then minus sine times minus sine. Let me write that here. Okay, so doing that one, cosine times minus cosine is minus cosine squared, and this will be minus sine squared, because you go minus this way. I'm pulling the minus sign out in front here. Then the cosine squared plus sine squared is 1, so I can replace this with 1 here. So let me simplify everything now. Okay, simplifying, we get this. So the pull the 2 out of the up here, and notice the double minus sign makes that positive there. So it'll be, let's write t cosine first, and then minus sine for this I component. And here I factor the 2 out, and then it'll be cosine plus t sine t. And this is 1, so you got a minus in front, so it'll be minus k. So that's our answer. Okay, so we're done with this example. Now let's move on to the next part, which is talking about integrals of vector valued functions. So I'm going to erase this now. Okay, so now let's talk about how to integrate a vector value function. So let R be a vector value function f1i, f2j, f3k, where f1, f2, and f3 are continuous. Then the indefinite integral of r of t is defined as, you basically just integrate the f1 guy, I direction, f2 guy, j direction, f3 guy, k direction. Moreover, the definite integral, so when you have numbers up here, you just put numbers on the f's, the integrals of the f's here. Okay, so it's a natural extension of the single variable integral. Okay, now let's look at an example here. So I'm going to erase this now and write up an example. Okay, so example, find the antiderivative of r prime equal to sine I 1 over t plus 1j t squared k. So to find r from r prime, we're just going to integrate. So we're going to integrate this guy, and this guy. So let's do it down here. So then r would be the integral of sine t dt, I direction, integral of 1 over t plus 1, j direction, integral of t squared k direction. Now integrating sine will become minus cosine, integrating t squared will become add 1 to the power t cubed divided by new power t cubed over 3. And integrating this, it's going to be ln of the absolute value of t plus 1. But I guess if we wanted to use a u substitution, we could here. So let's just see the u substitution we'd use here. Okay, so making the u substitution t plus 1, u equals t plus 1, then du dt will be 1, then du equals dt. So you can write this middle integral as just integral of 1 over u du. Let me write down the answers then. And we know that the integral of 1 over u is going to be natural log of u, actually natural log of the absolute value of u. So let's integrate this, and this right here. So integrating, we get minus cosines. When you integrate, you have to put a plus a constant here. That'd be I direction. So integrating this would be ln of absolute value of u, but u is t plus 1, so it's going to be ln of absolute value of t plus 1 plus a second constant, call it c2, j direction. Integrating t squared will become t cubed over 3 plus c3k. Now we need r of 0 to be 0, 3, minus 1. So we'll be able to find, and with this condition we'll be able to find the c1, c2, and c3. Let's first compute r of 0. So plugging 0 in place of t would have negative cosine of 0 plus c1, I direction plus ln of absolute value of 0 plus 1 plus c2, oops, should be j direction here, and plus 0 cubed over 3 plus c3 k direction. Now the cosine of 0 is 1, so it'll be minus 1 plus c1. The natural log of 1 is 0, so let me simplify this down here. So we end up with then negative 1 plus c1, and then it'll be just c2 here because that's 0, and then it'll be just c3 here. Now our r of 0 we want to be 0, 3, minus 1, so we should be able to find conditions on the c1, c2, and c3 that make that true now. So let's make an observation. Okay, so now r of 0 from up here is 0, 3, minus 1. That implies that 0 must equal to negative 1 plus c1, which I have here. That means that c1 needs to be 1. The c2 is 3, and the c3 would have to be minus 1. So let me write my final answer then right here at the bottom. Okay, so plugging in the c values up here, we'll get this. So this is our final answer right here. So this is our antiderivative that has the condition that r of 0 is 0, 3, minus 1. So we're done. Okay, so we're done with this section, so I'm going to leave the video here.